Okay, so this is the Math 150, just general review session. Any questions you have, just speak up whenever.
The first one I have is about the different kind of tests that we use. Like, can you show some examples?
Sure. So we have different types of convergence tests. And again, the way I like to view this is, baby is crying and you want to figure out why is the baby crying. You go through a bunch of things. After a while, you start to recognize from the crying what's the particular problem. When you don't know, however, you just try things one at a time. And if you are unsure about what order to try them, and if you have no idea, I would go from whichever test looks like it's going to be the easiest to try. So this is, tests for convergence. So the simplest, oops. Hello? Yes? Good, I'm in the middle of a review call with my students. Can I pay back in about half an hour? No problem. Okay. Sorry about that. Okay. Can you see the screen again?
Yes.
Okay, so the first is, does an tend to 0 as n goes to infinity? And so if no, it diverges. And by diverges, I mean the sum, say n goes from 1 to infinity of an. If the terms are not tending to 0, then that means you give me any small number, say 1 over a trillion, or 1 over a billion. There's got to be some small number that works. And infinitely often, you can find terms whose absolute value is that large or larger. So that means you're getting a sizable boost as you're going to infinity, and the sum can't converge. The only way the sum can converge is if the terms tend to 0. Now, if yes, it may converge. So for example, the sum of 1 over n diverges, but the sum of 1 over n squared converges. Just because the terms tend to 0 doesn't mean that the series converges. It just means you have a chance. Okay? So I think this is the simplest test to use. If you're lucky enough to see that the terms aren't tending to 0, then you know it has to diverge. If the terms are tending to 0, then you have to do more work. So the next one that's often worth trying is the comparison test. So if you have 0 is less than or equal to an is less than or equal to bn, and the sum of bn converges, then the sum of an will converge. And if 0 is less than or equal to cn is less than or equal to an, and the sum of cn diverges, then the sum of an diverges. So if you can find a good series to compare to, it's often very easy to tell if a series converges or diverges. The key part of that sentence is if you can find a good series to compare to. This is where it's more of an art. This is where it's almost the divine inspiration. This is where years of experience are beneficial. If I give you something, do you have an intuition as to whether or not it converges or diverges? If you think it converges, try to find something larger that converges. If you think it diverges, try to find something smaller. For example, let's say I give you, an is, 2 to the n plus 3 to the n over, n to the 4th plus 4 to the n. So do you think this converges or diverges? What are your thoughts? It's okay if you're wrong. Try something. Give me some thoughts. When you look at this, what makes you think it might converge? What makes you think it might diverge?
I think it might diverge
Okay, why do you think it might diverge?
because it looks similar to the one that's like 1 over n over 4. And when n goes to infinity, it goes to 0. So
Okay, so let's turn back to the comparison test. But actually, we have the following result. The sum of 1 over n to the p, n goes from 1 to infinity, it converges if p is greater than 1. It diverges if p is less than or equal to 1. And so I just gave you the specific examples here of p equals 1, which diverges, and p equals 2, which converges. So this is called a p-series. And that's because we have p as the power, p for power of n in the denominator. So this kind of makes sense. The larger p is, the larger the denominator, so the smaller the fraction, so the more chance it has of converging. The smaller p is, the smaller the denominator, which means the larger the fraction, so the more chance it has of diverging. So after saying that, when you look at this, what makes you think about converge? What makes you think about diverge?
yeah, it looks like the one that you showed before, so converges, but
Okay, so why do you think it might converge?
because p is greater than 1.
Okay, so p is greater than 1, so the n to the 4th makes you think that it might converge.
Yeah, but then the 2 to the end like confuses me. Like then it gets me thinking, but I think that that's irrelevant now.
Well, okay, but now you've pointed out that there's an issue with this problem. This is a hard problem. The numerator is exploding, right?
Yes.
The denominator is exploding. So it's being pulled in two different directions. The larger the numerator, the more likely it is to diverge. The larger the denominator, the more likely it is to converge. So we have to figure out, which do we think is growing faster, the numerator or the denominator, and by how much? So which do you think is going to really matter in the numerator, the 2 to the n or the 3 to the n?
I think that 3 to the end, but at the end of the day, like both of them will be very big.
Okay, but so the 2 to the n doesn't really matter. It's dwarfed by the 3 to the n. Okay? So do you agree that when n gets huge, 3 to the n is going to be tremendously larger than 2 to the n?
Yeah, I agree.
Now let's look at the denominator. Which do you think is growing faster, n to the 4th or 4 to the n?
4 to the end.
4 to the n. So what we could say is, if I just drop the n to the 4th, do I make things larger or smaller?
You make it smaller.
I make it smaller, which makes the whole fraction larger, right?
Yes.
So if I drop the n to the 4th, it's less than or equal to 4 to the n. So now if I want to have a less than or equal to, I want to replace the numerator with something that's larger. Well, if I replace the 2 to the n with 3 to the n, I've made the numerator larger. Right?
Yeah.
And so this would then be 2 times 3 to the n over 4 to the n, or 2 times 3/4 to the n. So do you think this is going to converge or diverge?
Now that looks like R, right?
Good.
Like 3 times R.
So it's a geometric series. The 2 doesn't matter. R equals 3/4. So it what converges or diverges?
Converges.
converges. Now, what I could have done is I could have tried to find something smaller, right? Maybe I think it diverges. I could have said, 2 to the n plus 3 to the n over n to the 4th plus 4 to the n. Well, let's try to find something smaller than this. Well, if I want something smaller, oops, I could replace the 3 to the n with 2 to the n. And if I replace the n to the 4th with 4 to the n, I'm going to make the denominator smaller, right?
Yes.
So that's going to be 2 times 2 to the n over 2 times 4 to the n. That's just 2/4 to the n. That's a geometric series which converges, but that doesn't help me because that's a lower bound. I've just told you that I have something that is going to be greater than or equal to something that converges. Well, that doesn't help me. If I want to show that it converges, I have to show that it's less than or equal to something that converges. So this is not useful. Does that make sense?
Yes.
So again, for some problems like this, before we start getting to the ratio test or the root test or anything like that, it might be better to say, well, look, do I have some intuition? The numerator looks like 3 to the n. The 2 to the n is really small. The denominator looks like 4 to the n. Oh, okay. 3/4 to the n, that would converge. So let me see if I can find something which is greater than or equal to this that converges. And that's where the intuition came from. Okay, so let's go to the next. The next one we have is the integral test. Now, say, an is non-increasing. Let's say, f of n equals an, and f is non-increasing. Then the sum, n equals 1 to big N of an, is approximately the integral from 1 to big N of f of x dx. And we talked about how to prove this using Riemann sums. And so if an is a non-increasing function, this gives us some hope. So for example, let's consider the sum of 1 over n log n goes from, say, 10 to infinity. Why do you think I don't want to have n equals 1? What would happen if I put in n equals 1? What is 1 times the natural log of 1?
Is it 0?
It's 0. So if I put in n equals 1, it blows up. So I have to technically start at 2. And so just to be safe, I'm going to just throw away the first couple of terms and I'll start at 10. So when you look at this, your first thought is, do the terms go to 0? Yes. We know 1 over n goes to 0. Is this going to be larger or smaller than that? So do you think this is going to be larger or smaller than the series 1 over n?
Smaller maybe?
It's going to be smaller. We're putting this extra factor of the log of n. As n goes to infinity, the log of n goes to infinity. So we're making the denominator smaller. So if 1 over n is going to 0, this goes to 0. So unfortunately, this means I can't use the simple test, do the terms go to 0? Because the terms do go to 0, so I have no information. I could try to compare this to a series. Well, if I compare this to 1 over n, unfortunately, 1 over n is larger, right? So I know that this is less than or equal to a sum that diverges. That gives me no information. If I want to show it diverges, I have to show that it is greater than something that diverges. If I want to show that it converges, I have to show that it is smaller than something that converges. This is larger than 1 over n squared. And it's smaller than 1 over n. So it's not clear what to do. So can you think of what would be a good function f of x to try? So what would be a good function f of x such that when you take x equals n, you get 1 over n log n?
Is it like 1 over x log x?
Yeah, the rule is basically replace n with x. That's how you find the function. So this is approximately the integral from 1 to, let's say 10 to n of 1 over x log of x dx. So we have to figure out how to do this integral. So in the interest of time, I'm going to use some divine inspiration. I'm going to do a u substitution. I'm going to let u equal the natural log of x. So what would du be? It would be 1 over x dx. As x goes from 10 to infinity, u is going to go from the natural log of 10 to infinity. And so this integral becomes u goes from the natural log of 10 to infinity. Now 1 over log of x, that becomes 1 over u. 1 over x dx becomes du. Does everybody see how I got this?
Yes.
So what function has derivative 1 over u?
ln.
Yep, so this would just be the natural log of u evaluated at the log of 10 and infinity, and that's just going to be infinity, so it diverges. So 1 over n log n diverges. As a nice exercise, try the sum n goes from 10 to infinity of 1 over n log of n squared, and you'll get that this converges. So that's a really good exercise for you to do to see if you can figure out how to generalize the integral test. And so it's telling you that there's not that much of a difference sometimes between a series that converges or diverges. The log of n is a very slowly growing function. 1 over n log n diverges, 1 over n log squared n converges. And there's a great series of exercises in a classic book, Rudin, Principles of Mathematical Analysis, where they play games like 1 over n log n, log n, whole thing squared, and just trying to find just how far you have to go to see converge, diverge. So this is the integral test. And again, the key point is you basically replace n with x. Then we have the ratio and the root tests. So the ratio test is let's let rho equal the limit as n goes to infinity of an plus 1 over an in absolute value. And then if this is less than 1, it converges, equals 1, no info, greater than 1 diverges. What's really going on is the ratio test is secretly a comparison test with a geometric series. That's why you see such a similarity. When it's less than 1, it converges. When it's greater than 1, it diverges. What's the hardest part of using the comparison test? What makes using the comparison test so difficult?
Makes the algebra very bad.
Okay, and it's doing the algebra to compare it to something. to show that this is less than this or this is greater than that. The whole point of the ratio test and the root test is they're secretly comparing it to a geometric series for you, and they're figuring out which one to compare it to. So you get the benefit of the comparison test without having to figure out what to compare it to. The disadvantage is it has to compare it to a geometric series. It doesn't give you as much flexibility to compare. But for a lot of things, this is going to be fine. Let's say I give you, an is n cubed over 3 to the n. The terms tend to 0. Is 3 to the n growing faster than n cubed?
Yeah.
Yeah, 3 to the n is growing much, much faster. That's growing exponentially fast. N cubed is only growing polynomially. So this has a chance of convergence. We now calculate rho. Rho is going to be the limit as n goes to infinity of an plus 1 over an in absolute value. And yeah, I have to keep writing the word limit each time because I'm not doing 6n. It would be n plus 1 cubed over 3 to the n plus 1 over n cubed to the n. The limit of n goes to infinity. I'll do it very slow. 3 to the n over 3 to the n plus 1, n plus 1 cubed over 3 cubed. The limit of n goes to infinity is 1/3 1 over n. 1/3 goes to infinity. What does n plus 1 over n go to?
0.
Sorry? I couldn't hear you. What
Oh.
does n plus 1 over n go to? Could you speak up again?
Is it 1?
Well, it's 1. Yeah, if you think about what's going on, we have, say, 101 over 100, 1,000,001 over 1,000,000, 1,000,000,001 over 1,000,000,000. The difference is getting smaller and smaller and smaller in terms of how much this exceeds 1 by. You can write this as, this is just 1 plus 1 over n, and as n goes to infinity, 1 over n goes to 0. So this is just 1/3. So does this converge or diverge?
No, it converges.
It will converge. And then the last test, and this is the hardest one to use, is the root test. It's very similar. Rho is going to be the nth root of an. Oops, what did I forget here? What did I forget to write?
Limit.
I forgot to write the limit as n goes to infinity. Here I says the limit as n goes to infinity of an to the 1 over n. And if this is less than 1, it converges, equals 1, info, greater than 1, divergence. This is again very similar to the root test. The real difference is the algebra becomes a little bit harder. And so one of the key facts to note is n to the 1 over n goes to 1 as n goes to infinity. So we talked about the proof of that in class. The easiest way to see this is let's study the log of n to the 1 over n and show that goes to 0. Well, this is going to be 1 over n times the log of n, or the log of n over n. So if I want to take the limit as n goes to infinity of the log of n over n, I have infinity over infinity. So what should I do?
Root test.
Can't do the root test here.
Do you take the derivatives of both?
L'Hopital.
Yeah, so what's that called when you take the derivative of the top and the derivative of the bottom?
L'Hopital's.
L'Hopital. You know you've made it when your name becomes a verb. So you L'Hopital it. Okay. And then that would be the limit as n goes to infinity. What's the derivative of the natural log? The natural log of x, what's its derivative?
1 over x.
And so I'm just using n as my variable, so this just becomes 1 over n. The derivative of n is just 1, so that limit is just 0. So since the log of my quantity goes to 0, n to the 1 over n goes to 1. So this is an extremely useful fact to know when you're trying to do root tests. And if I have something like n to the 1 over n, for example, if I give you, an is n cubed over 3 to the n, what would be the limit as n goes to infinity, n cubed over 3 to the n to the 1 over n? That's the limit as n goes to infinity of n to the 3 over n, 3 to the n over n. That's the limit as n goes to infinity of n to the 1 over n cubed over 3. So that's just 1/3 the limit as n goes to infinity of n to the 1 over n cubed. And that's just 1/3 less than 1, so it converges. And so, to do this using the root test, I needed to know that n to the 1 over n converges to 1. And so if I square it, well, if something is going to 1, its square goes to 1. If I cube it, it will still go to 1. I'm just raising it to a finite fixed power. So these are the 5 basic convergence tests we know. There are, a lot more tests you can learn in an advanced course, but this is enough to get a sense of, does the series converge? And one of the reasons we care about this so much is when you have a complicated function, we like to replace a complicated function with a sum of simpler functions. And this is a general idea in mathematics. Take something complicated and turn it into a lot of easy things. So any other questions about, series and convergence?
Not really, thanks.
Okay. Any other questions?
I don't fully understand like spherical coordinates, like the second. I can't remember that variable. It's not theta, but like I don't really understand what's going on.
So for spherical coordinates, we start with an x, y, z, and we move back and forth to a rho, theta, phi. So think of rho as how far you're traveling from the center of the Earth. Think of phi as your, I always get the latitude, longitude mixed up. Is the latitude the one that is parallel to the equator?
I think so.
Okay, so then phi would be the latitude and theta would be the longitude. And this is trying to tell, where you are on the point of a sphere. And again, I can represent a point in 3 space either as, an x, y, z coordinate, or I have the origin. I tell you how far out I travel, that gives me a sphere. And then I just tell you how far down I come from the North Pole, and then how far around I rotate parallel to the equator. So you give me any point, it has a fixed distance from the origin. That's going to be my rho. And then I just figure out my theta and my phi. So rho is the easy one. Rho is the square root of x squared plus y squared plus z squared. It's how far you are from the origin. And if you're trying to think about what's going on, so you say here's x, here's y, here's z. I start coming down some angle phi, and then I'm going to go parallel to the xy plane, some angle theta. And so for phi goes from 0 to pi. I go from North Pole to the South Pole. Theta, goes from 0 to 2 pi. This is parallel. That's a terrible parallel. To equator. Okay. So what you're doing is you have a circle that's in the xy plane, but just shifted up some height. And then the question is, what is that height? Well, when I come down like this, I can figure out what z is. Z is just going to be rho cosine phi. That's going to tell me how high up I have moved. And then this number over here, I'll call this r, and we'll get r is going to be rho sine phi. And so the whole point now is we now have polar coordinates with r is equal to rho sine phi and theta. Well, we know in polar coordinates, x is equal to r cosine theta, y is equal to r sine theta. So this becomes x is equal to rho sine phi cosine theta, and y is equal to rho sine phi sine theta. And this gives you how to pass from x, y, z to rho theta phi. And this is why we like to use phi as the angle coming down from the z-axis, because then it sets us up nicely to do spherical coordinates. So if you think about it, if you're in three-dimensional space, how many variables should it take to describe where you are?
3.
It should take 3. And so, the standard way, this is like the Manhattan way. I have my north, south, my east, west, and now we'll add up, down for, what floor we're on in a building. And so in Manhattan, Cartesian coordinates would be really good. Your x, y, and then your z is going to be your height. But if you're on the Earth, spherical coordinates make a lot of sense. How far are you from the center of the Earth? And then what's your latitude? What's your longitude?
Yeah, thinking about it as like the center of the Earth really helped.
Yep.
Thank you.
So it's we have a special point and we're doing it from there. Now, if you look at what's going on, the spherical coordinates actually break down at the origin. Because if your radius is 0, then theta and phi can be anything. So you no longer have a unique change. You no longer have one XYZ corresponds to one rho theta phi. There's actually infinitely many rho theta phis that work for 0, 0, 0.
Oh.
It's a bit annoying, but it's not so annoying that we throw away spherical coordinates. So many things have spherical symmetries, and if you take physics, you're not allowed to be at the origin. If you have a point mass there, you can't occupy the same space as something else. So you're never going to have two things in the same spot. So we don't have to worry about that. All right, we've got about another 10 minutes. Any other questions?
Yeah, I was just confused by well, I guess the topic as a whole doesn't confuse me because it's very straightforward. But the several vector questions that we got on the exam, transform or just how to remember what to do in every situation, I guess, for vectors.
Mm-hmm. For like equations of lines and planes and whatnot. Or what is the question?
Yeah, when you ask about like transformations or like, I don't know, like that's like the only thing that's coming to my head right now. But like,
Well,
yeah, just like the
I didn't really
the-
ask about transformations. I asked you more about,
like
find the equation of a
the
line
form,
going through
right?
a point in a direction, or
Yes,
find a
yes,
plane. So
yes.
you just have to either remember these or you have to rederive them.
Okay.
And so, if I give you, equations of lines, planes, ... So let's say we have, some three-dimensional coordinate system. I've got some point here, P, and I've got some direction, V. Oops, let's have that in a different color. I can then find, here's the line. Whoops, it's not changing color. Here is the line going through V going through P in the direction P. So line through P in direction V. So what is the dimension of a line? How many dimensions does a line have?
1.
Does the line have 1 dimension, 2 dimensions, 3 dimensions, 1.6 dimensions? How many dimensions does a line have?
1.
1. So I should just have one free parameter that tells me where I am. And so what I can do is I can have, some point at time t would be my initial point, P, plus t times V. Or if you want x of t, y of t, z of t, is my initial point, px, py, pz, plus t times vx, vy, vz. And if you think about it, when you take t equals 0, we get p times 0 is just our initial point. When t equals 1, we get p of 1 is just p plus v. We've just flown along. We've just flowed along, in the direction of v. We've gone one multiple of v along. And so this is going to trace out a line, based at a certain point, going in a certain direction. So this is probably the easiest way to write the equation of a line, with a given point and a given direction. If I give you 2 points on the line, can you calculate the direction? So say I want, the line through, P1 and P2. Well, we could let V be P2 minus P1. And then the equation would just be, P of t would just be, say, P1 plus t times V. And so if I give you 2 points, here's how you could find the equation of a line. So after you have the equation of a line, the next is the equation of a plane. And so again, as before, let's say I have some point, P, and now how many directions do I have to give you for a plane? So a line was a one-dimensional object. What's the plane going to be?
2.
2. And so maybe I give you 2 vectors now, say maybe here's V and here's W. And I'll look at the plane going through P with these as my 2 directions. And I'll get my point, and now I'll have 2 parameters, T and S, would be my base point P plus T times V plus S times W. And if you think about it, if you set S equals to 0, this reduces to just a line. Similarly, if you set T equal to 0, it reduces to a line. And so now this is flowing in 2 different directions. And so this is one way to write the equation of a plane. And then if I have a hyperplane, if I have something in four-dimensional space, I might give you a UVW. Now, in three space, we do have the normal form. And so, and then after this, I'll take one more question and I've got to go. So let's say, again, I have my coordinate system. I have my point P. And now let's say I give you a normal direction. So here's my normal. And I want the equation of the plane that has any normal. So think about what's going on. If I give you any point in the plane,
Professor, I don't know if it's just me, but your audio is.
Okay. Is
Oh,
this
yeah.
better? Okay.
It's better, yeah.
Okay. So let me give you some point in the plane. So here's my point P of t. And then I can look at this vector over here. So this vector is going to be P of t minus P, and that needs to be perpendicular to n. So how do you tell if two vectors are perpendicular?
When their product is 0, I think.
Yeah, when the dot product is 0. So we can look at n dotted with P of t minus P equals 0. Is that 0 the number or 0 the vector?
The number.
0 the number. And so then that would be the same as, say, n dotted with P of t is equal to n dotted with P. So if n equals, say, A, B, C, and P of t is x of t, so I should not be using t, I should just be using some point. And P is just x, y, z, we would get ax plus by plus cz is d, where d is equal to n dot your initial point P. So this is another way to write down the equation of the plane. And a lot of it comes down to just, well, what information do you have? If you happen to have the normal direction, then you're lucky. If we know, V and W are in the plane and not parallel, then V cross W and the normal are in the same direction. So this is another way, depending on what I give you. If you like writing things using a normal, well, if I give you two vectors V and W, you can calculate the normal and then you can just do the dot product. And now I've got things in terms of X, Y, and Z. How many dimensions does a plane have? Two. And so if you look at it, I have AX plus BY plus CZ equals D. You might think at first that you have three free variables, X, Y, and Z, but because you have this one equation, it allows you to solve for one of them in terms of the other two. So you really only have two free variables out of the X, Y, and Z. This is similar to how a moment ago, we only had two free variables, T and S. So even though it looks like I might have three variables, X, Y, and Z, once I know two of them, the third is determined. All right, so if anybody has one last question, if you haven't asked a question yet, you get to go first. If not, I will open it up to anyone. Okay, any final questions?
I just had a quick one because you just mentioned like 4D space. Is it possible to like visualize that, or can you only do that like with algebra?
There are, I mean, the best way is really through algebra. What you can try to do is you can try to use color to try to give you another dimension. So for example, if you look at a two-dimensional map of the United States, what you want to do is maybe you want to look at a heat map. You want to look at what are the temperatures. Well, the temperature could represent maybe your vertical height. And I color the US based on what the temperature is. So maybe the hotter it is, the more red it is, the colder it is, the more blue it is. I'm now representing this three-dimensional object by using color and doing this in just a two-dimensional flat image. So then you could play that same thing in three-dimensional space. If I wanted to try to represent a fourth dimension, I could then color points in three-dimensional space and use that color to try to give me a view of the fourth dimension. It is not easy. And this is one of the reasons why, certain things in mathematics become really hard to get intuition for, because it's hard for us to visualize. We have no trouble visualizing two dimensions and one dimension going down. We can actually play some pretty good tricks and represent three dimensions on a two-dimensional surface. So have you ever seen a three-dimensional object represented on a two-dimensional surface? And if so, where?
I guess like a map of the Earth, like you said.
Yeah, there's a map of the, but there's a better example that you've seen almost every day in your life because you live in the 21st century. Where would you see something three-dimensional represented on a two-dimensional surface?
Is it like if you open something on your phone?
Yeah, if you watch any streaming video, right? That's a three-dimensional object, but it's being represented on a two-dimensional surface. Your phone is flat. Your phone is not this hollow box where you have these three-dimensional photons. It's a flat surface, but things are done in such a way that you feel like you can see depth. I unfortunately have to run now. I will post these later. Have a great rest of the break, and I will see you all on Monday.
Thank you, Professor.
Take care. Bye-bye.